Hello, my name is Ana Cecilia Valdez, and this is my lab 5 for Physics 2212 Magnetic Braking with Faraday. For this lab, the main purpose was to retrieve observational data from the scenario in which a magnet falls through a tube of aluminum foil. Also, to model this interaction computationally, and finally, to compare the computational predictions with the observed data. So a preview of my results is that the actual average time taken for this to happen was of 1.48 seconds versus the computational time being of 1.54 seconds. The key concepts that were used in this lab are the following: Faraday's law, Ohm's law, Biot-Savart law, magnetic field of a bar magnet, magnetic flux, and the momentum principle. So as you can see, these are three formulas that we will be using later on for the calculations of the lab. So the procedure for this experiment consists of mainly 5 parts. First, identify which side of the magnet is north. Then, recording, dropping the magnet through the aluminum foil tube. Then, scrubbing through the video to find the entry and exit times of the magnet. Then, repeating this process 5 times. And finally, taking all of the information retrieved to find the average time taken for the magnet to travel through the tube. After performing the multiple steps that I explained in the last slide, I retrieved the following data. The length of the tube in my experiment was of 0.3 meters or 3 centimeters. The inner radius of the tube was of 0.2 meters. The foil width was of 0.01 meters. The magnetic dipole moment of the magnet was of 3.31, and the magnet mass was of 0.0233 kilograms. So for the computational model of this experiment, the first step was to declare the variables. As you can see, we have mass in kilograms and the magnitude of the magnetic dipole moment, which we got from lab 3. And we'll just a code to visualize the bar magnet. Then for the second step, we created a function that calculated the magnetic field of the bar magnet. As you can see, the first step was to take the magnitude of the r vector and then the r hat, which is just the r vector over its magnitude, and then finally with the formula that I explained before, we took the magnetic field of the bar magnet. Then for step 3, I created a function that calculated the magnetic flux, again based in the formula that I explained before, and here's the code. Well, and then for the next few parts, first we calculated the gravitational force on the magnet, as you can see here, which was just a vector for in which we consider the mass and the gravitational acceleration constant. Then for the next step, we calculated the current in the ring, and then we calculated the typical B field at each ring, and we did this considering the magnetic field to be axisymmetric. And here we have the magnetic field at the ring, the B hat, and the magnetic field on the ring and on the magnet. And well, then we calculated the net force on the magnet, which is just the gravitational force, the force of gravity, sorry, plus the force of the magnets. And we calculated finally we updated the magnet's velocity and position with the velocity of the formula and the position of the formula. These are the results that I got from the computational model. Well, interpreting the results, I can say that first, it's important to know that the red corresponds to the counterclockwise current, while the blue corresponds to the clockwise current by Lenz's law. And well, this is what creates the force that slows down the magnet, which was like the whole point of the experiment. And when you flip the magnet around, the dynamics of the system don't change, but since the current flows in the opposite direction, we get a different time. And well, the models were accurate. However, I could improve them if I split the tube into more rings to get more accurate results. And the graph that I showed in the previous slide show us that the forces acting on the magnet are not balanced, where it is not constant. Now, to conclude this video, answering some what if questions. If the resistivity of the conductor was reduced as close as possible to zero, what would be the change in the dynamics of the falling magnet? Well, what would happen would be that the braking force would increase, matching the force of gravity, and then preventing the magnet from falling through the tube because the induced current would be approaching infinity. And well, what if the holes or slots were cut into the tube? This would affect the ring currents in our model, as there would be less current flowing and braking force would be weaker, causing the magnet to fall faster.